Hello everyone and welcome to a new experiment video. In this video I'm going to test out the kinetic energy formula. So I'm first going to show you the setup. I have a bar which is 1 meter long, okay, and at the end I have a spring attached to the wooden block. The bar is connected with the wooden block. I have 4 of these wooden balls slided over the bar. First I'm going to launch this one wooden ball. So this is once the mass. At the bottom of the wooden ball I have a little flag that measures 1 centimeter. The width of the flag is 1 centimeter. And that will pass through this timer over here. This is the timer. Okay. So I will launch it. I will try to compress the spring all the way to the end and then launch it. And then we're going to measure, well, the timings will be showed on this display. And then we will know how long it took for the card, for the flag to move through the photo gate. And that will indicate the velocity. And each time I'm going to compress the spring all the way to the end so that we can be sure that it will always be the same amount of energy input that will be given. So first I'm going to do a couple of launches with one's the mass. Then I'm going to add another wooden ball, which is going to be twice the mass. Okay. Then I'm going to do the same with 3 times the mass. Compress it all the way and launch it. And then finally I will do the same with four times the mass. 4 times as heavy. And then launch it. Okay. Here we have the theoretical predictions. So we have energy equals 1/2 times the mass times the velocity squared. So the energy input is always going to be the same. I'm going to compress the spring always to the very end. So the energy input should always be pretty much the same. So let's say that the energy input is 100 joules. Then for the one mass, so this is, let's say that the one mass is 10 grams, then twice the mass 20 grams, 3 times the mass 30 grams, and 4 times the mass 40 grams. So if this is the mass for the one mass, and this is the amount of energy, then the velocity should be around 4.47 meters per second. I forgot to include the unit over here. So then it's going to be around 4.47 meters per second. Then if we're going to double the mass, then the velocity should be around 3.16 meters per second. So which means that the 2 mass should be going 1.41 times slower than the 1 mass. Okay, then for 3 mass, for 30 gram, and the same energy input, the velocity should be around 2.58 meters per second squared. 2.58 meters per second. And then, which means that the 3 mass should be going around 1.73 times slower than the 1 mass. And for the 4 mass, with the same energy input, the velocity should be around 2.23 meters per second, which means that it will be twice as slow as the 1 mass. So we're going to verify that. But before I continue, I also want to show you the alternative model. There are people who claim that kinetic energy is not real, that it doesn't exist. Instead, they believe that energy equals mass times velocity, which is momentum. They believe that momentum is exactly the same as energy. Okay, if that's the case, then for their predictions for this model is, so the same energy input, and for the 1 mass, then the velocity should be around 10 meters per second. For the 2 mass, with the same energy input, the velocity should be around 5 meters per second, which means that the 2 mass should go twice as slow as the 1 mass. Not 1.41 times as slow, but twice as slow. And for the 3 mass, the velocity should be around 3.33 meters per second, which means that the 3 mass should go 3 times as slow as the 1 mass. Not 1.73 times as slow, but 3 times as slow. For the 4 mass, the velocity should be around 2.5 meters per second, which means it should be going 4 times as slow as the one mass. Not 2 times as slow, but around 4 times as slow. So I'm going to do the physical experiment, and then let's see which model will win. Okay, so let's start with the one mass. You can follow along with the timings over here. So this is the first trial. That was around 12. 12 again. Then I can let it release. Okay, these are the results. These are the fastest velocities I was able to produce, because there is always going to be a little bit difference in launching the balls, because I'm using my fingers, and the way I put my fingers on the ball and compress the spring is also going to be a little bit different, a little bit of a difference. But these were literally the fastest velocities I could get. None of them produced any faster than this. So, and the fact that I have quite a bunch of similar results should be trustworthy data collection. Okay, so for the one mass, we mostly had around 0.0012 seconds. For the two mass, or the same energy input, we mostly had around 0.0017 seconds, also 0.0818. For 3 mass, mostly around 0.0021 and sometimes 0.0022 seconds. For the 4 mass, it varied between 0.0023, well, this was only once. Twice I got 0.0024, but mostly I had 0.0025 seconds. So now, let's compare it with the theoretical predictions. So normally the 2 mass should go around 1.41 times slower than the 1 mass. And when we do 17 divided by 12, that's exactly what we get. We get a 1.41 result. It's a perfect result. Really spot on, perfect result. The 2 mass went 1.41 times slower than the 1 mass. Then the 3 mass normally should go 1.73 times slower. My result is, so mostly 21 divided by 12 equals up 1.75. So 1.73, 1.75, very, very close. And then for the 4 mass, so normally it should go twice as slow than the 1 mass, and I got, so mostly 25. 25 divided by 12 equals 2.08. So again, pretty close to 2. So it seems like, well, it doesn't seem like, it's pretty obvious that the kinetic energy formula is correct. Kinetic energy is real, it's a real phenomena. I got pretty perfect results. So the theoretical predictions and the practical physical evidence, they match almost perfectly. So physics works, people. Physics works.